Hello, curious minds! Welcome to G Champion. Today we're diving into the fascinating realm of fluid dynamics, exploring the differences between steady and turbulent flow. Get ready for a journey through the mesmerizing movement of liquids. Now, you might be wondering, what exactly is fluid dynamics? Well, in the simplest terms, it's the study of how liquids and gases move. Picture a stream of water flowing down a mountainside, or the wind gusting through a valley. These are examples of fluids in motion, and fluid dynamics helps us understand the forces and factors that influence this movement. At the heart of fluid dynamics is the concept of flow. When we talk about flow, we're referring to the movement of the fluid, be it liquid or gas, in response to forces like gravity, pressure differences, or even temperature changes. The way these forces interact with the properties of the fluid, such as its viscosity or density, determines the nature of the flow. Now, one of the most fascinating things about fluid dynamics is the range of flow behaviors we can observe. On one end of the spectrum, we have steady flow. This is when the fluid moves in a smooth, predictable manner, like the calm currents of a gentle river. On the other end, we have turbulent flow, where the fluid moves chaotically, full of swirls and eddies, like the rapids of a raging river. Understanding the difference between these two types of flow is crucial, not just for scientists, but for anyone who's curious about the world around them. After all, we encounter fluids in motion every day, from the water we drink, to the air we breathe, and even the blood flowing through our veins. Fluid dynamics is the study of how liquids and gases move. One crucial aspect is understanding the difference between steady and turbulent flow. Let's break it down. Imagine a gentle stream flowing smoothly without disruptions. That's steady flow for you. Picture the tranquility of a quiet brook, the water moving along its path with an unchanging speed and direction. This soothing, predictable movement is the essence of steady flow. In the world of fluid dynamics, steady flow is the ballet dancer of the liquid realm. It's graceful and consistent, moving in an almost choreographed manner. Each particle of the liquid follows a path that other particles have taken before and will take again. There's a certain peace in this predictability, a calm that's mirrored by the quiet babble of a serene stream. When we talk about steady flow, we're talking about a situation where the velocity of the fluid at a given point doesn't change over time. In simpler terms, the liquid's speed and direction stay the same. It's consistent, reliable, and yes, steady. Now you might be wondering, where can we see steady flow in action? The answer is everywhere. From the slow drip of a leaky faucet to the gentle flow of syrup on your pancakes, examples of steady flow are all around us. But it's not just about the everyday. Steady flow is also an important concept in various fields of study and industry. Engineers, for example, use the principles of steady flow when designing systems where fluids need to move in a controlled and predictable manner, like in water supply networks or oil pipelines. In the grand dance of liquid dynamics, steady flow might not be the most exciting performer. It doesn't have the wild energy of turbulent flow or the dramatic twists and turns of a vortex. But it has its own charm, its own rhythm. It's the quiet beauty of a consistent, uninterrupted flow, the serenity of a liquid in perfect harmony with its surroundings. Steady flow is characterized by a predictable and continuous movement of the liquid, almost like a serene dance. Now, let's add a bit of excitement. Turbulent flow is dynamic, chaotic, and filled with energy. If we were to compare the steady flow to a calm, composed symphony, then turbulent flow is the high-octane rock concert. It's all about drama, energy, and a certain unpredictability. In the world of fluid dynamics, turbulent flow is like the wild child. It refuses to follow a straight line, preferring instead to mix things up with a flurry of eddies and whirls. It's a spectacle of irregular motion, with the liquid particles constantly changing their speed and direction. Imagine standing at the edge of a waterfall. You can hear the deafening roar as water crashes down, creating a misty spray. The water doesn't just fall straight down, does it? It cascades, it churns, it sends up sprays and creates whirlpools. That's a textbook example of turbulent flow. Or consider a fast-flowing river, especially after a heavy rain. The tranquil, predictable flow is replaced by a powerful, almost furious rush. The water swirls, it foams, it dashes against the rocks, creating a chaotic pattern of movement. Again, that's turbulence in action. Turbulent flow is not just about the spectacle though, it's an essential mechanism in nature and technology alike. It enhances mixing, increases heat transfer, and even influences the weather patterns around us. Interestingly, turbulent flow is also a bit of a mathematical mystery. Despite centuries of scientific study, fully predicting the behavior of turbulence remains one of the greatest unsolved problems in physics. But that's what makes it so intriguing, doesn't it? So, the next time you see a waterfall or a raging river, take a moment to appreciate the drama of turbulent flow. It's more than just a visual spectacle. It's a dance of energy and chaos, a testament to the dynamic and unpredictable nature of our world. Picture a roaring waterfall or the swirls in a fast-flowing river. That's turbulence in action. The transition from steady to turbulent flow depends on factors like velocity, viscosity, and the shape of the object in the flow. When we talk about velocity, we mean the speed at which the fluid is moving. High velocity tends to induce turbulence, making the flow unpredictable and chaotic. Imagine the fast-paced rapids of a river, where the rush of water creates an energetic display of turbulence. Now, let's discuss viscosity, a term that describes a fluid's resistance to flow. Picture honey and water. Honey, being more viscous, flows slower than water. In fluid dynamics, a higher viscosity often leads to a steadier flow. It's like the honey of the fluid world, flowing smoothly and predictably. The shape of the object in the flow also plays a crucial role. Think about the difference between a sleek, streamlined dolphin and a bulky, square container. The dolphin, with its curved and smooth shape, allows water to flow around it with minimal disruption, maintaining a steady flow. On the other hand, the square container disrupts the flow, creating areas of turbulence around its sharp edges. Temperature also plays a role in influencing the flow. As temperature increases, the viscosity of the fluid decreases, which can lead to turbulent flow. It's like turning up the heat in a drama. Things get more intense and unpredictable. Lastly, the size of the conduit or passage through which the fluid is flowing can influence the type of flow. A larger conduit allows for a faster flow, which could result in turbulence, while a smaller conduit might maintain a steady flow. So, as we can see, the transition from steady to turbulent flow isn't random. It's influenced by a fascinating interplay of factors like velocity, viscosity, shape, temperature, and the size of the conduit. And each of these factors can dramatically alter the behavior of the fluid. It's like nature's way of keeping things interesting. Understanding these flow patterns isn't just for scientists, it has real-world applications. The beauty of fluid dynamics lies in its ubiquity. It's not just confined to the realms of academia, but it permeates our everyday lives, shaping industries and technologies we often take for granted. Consider the engineering marvels that are our city's water supply systems. They rely heavily on understanding steady flow to ensure clean water reaches your taps efficiently. Without this knowledge, we could be dealing with burst pipes and wasted resources. Now, let's shift gears and dive into the world of aerospace. Ever wondered how airplanes manage to stay up in the sky? It's all about controlling turbulence. Engineers study turbulent flow to design wings and engines that can withstand the chaotic air currents at high altitudes. Moreover, in environmental science, understanding these flow patterns aids in predicting and mitigating the effects of natural disasters. For instance, understanding how water flows during a flood can help design effective evacuation strategies and save countless lives. But it's not just about the big picture. Even in our kitchens, the understanding of turbulence aids in the efficient mixing and heating of fluids, enhancing our culinary endeavors. From designing efficient pipelines to enhancing mixing processes, fluid dynamics plays a crucial role in various industries. So the next time you turn on a tap or watch a plane soar, remember, it's all flowing smoothly thanks to the fascinating science of liquid dynamics.